I would like you, based on what we did yesterday, to set up the integral that finds the volume when I take this shape, rotate it around the x-axis. So when we set up these integrals, in this case, if I'm rotating around the x-axis, I need a radius. I'm going to make a rotation. I'm going to have another picture down here. I take a radius, it rotates around, and this shape is a circle whose radius is that's the area. What's the radius itself? You're right that the area is pi r squared. But what's our radius for that? Yes. Right, it'd be a y value, but in this case, our y value is given here. So pi r squared. Now we're adding up little thick coins, little cylindrical slices. So I have to take their thickness into account. Where do I start and end this integral? It is from 0 to 2, because those are the leftmost and rightmost x values involved in this problem. Now here's a twist. I want to do the same thing, but I want to go around the y-axis. If I'm going around the y-axis, that means I'm going to flip this over to here. Right? And if I'm going to do this, I need to slice this differently. How do I slice this differently? Based on what we did yesterday. If it helps, turn the picture. I'm going this way. Yes? So that means I need to cut here and spin this around. Turn my picture back. And what I get this time when I pull this slice out is a washer. Problem. The washer has two radii, an inner radius and an outer radius. The inner radius would go from here. Actually, let me change colors again so we can see it better. The inner radius would go from the y-axis to the curve closest in. That's R in. The outer radius would go out here. But now, Jack, I have the reverse issue we had before. What's my R in this case? It's an X, not a Y. Because we're measuring horizontally, that's an X value. Well, technically, this is the X that's further to the right, and this is the X that's further to the left. But here's my problem. The equation involved was written this way. And I would need to rewrite that to be X equals. Now, I'm going to tell you right now, solving this equation for X is not worth it to me. Because it requires me to have either Cardano or Tartaglia's formula for solving cubic equations memorized, and it's going to involve the cube roots, potentially of negative things with square roots underneath them. No, just no. I don't want to do it. So this is a problem. I've only drawn one slice, but let's picture what this shape really looks like. I'm going to go back up. We have this curve, and we're spinning around this way, right? Any of you go to lunch yesterday in the cafeteria? I saw this shape in the cafeteria. If I spin this around, I get this shape. A cake. Didn't quite have the hole in the middle that the oatmeal breakfast cake usually looks. It's a bundt cake. But I can't cut this horizontally. I don't know how to make the slices work right. So my problem isn't the fact that I can't see the shape. My problem is this cut up method doesn't work. So I need to slice this up differently. And I mean that literally. I'm going to slice this in a different way. And it's not going to look like the slices that they make in the cake in the cafeteria. I went to the baking supply section. And I got cookie cutters. Here's what I'm going to do. Instead of cutting this way, I'm going to cut this way. I'm going to punch out a layer. And then I'm going to punch out another layer that's just a little bit bigger. I know these are scalloped. Let's use the flat sides. So really, the piece of cake I'm going to get is going to be the shape between these two circles. It's kind of like this, but I stood it up this way. So instead of cutting horizontal rings, I'm punching out vertical cylinders. Let's draw the picture a little better. Well, a little better is a relative term. Here's my curve, here's its reflection. Instead of cutting across, I'm going to cut up and down. So my slice on this side in the original curve is going to go this way, just like it did before. But instead of spinning that around the x-axis, I'm going to spin this around the y-axis. Do you see how I've made a cylinder here? I took this vertical stick and spun it around like a ribbon standing on end. Literally like that. Jordan, the other image is the band in your hair, right? A cylinder of fabric. We've seen these before. A thin little stick spun around in a ring. Okay. But I said I was going to do two of them, right? So I've got this little thin region between these two rings. Let's think about the volume of this like it was a slice. And if it's a slice, then I can add up all my slices and I can integrate. So, what is the formula for the volume of this thin cylindrical shell? Normally, when I ask for the volume of a cylinder, what's the volume of a cylinder? We did this yesterday. But that gives me the volume inside the cylinder, right? That's the entire inside, and I don't want the inside, I just want the edge. So let's picture our cylinder. I've rolled up a sheet of paper here. And imagine, I'm not asking for the area, the volume inside, I'm asking for the volume of the sheet of paper itself. I'm going to cheat. I'm going to take this sheet of paper and unroll it. And think of the volume this way. This is a box. What's the volume of a box? Length, width, height. Because I'm going to picture the box laying flat. Okay, wait a minute. The width of the box, that's going this way. The length of the box, that's going this way. Isn't that around the circle? If I take this and I unroll it, I get a rectangle. And so its area is length times width, but the length here is the length of this circle. That's a circumference. What's the formula for the circumference of a circle? And then this part, well, that's the height, isn't it? That's a y value again. But our y value is given by our function. And so the volume will be length, circumference. I'll write it that way. Circumference times height times thickness. This little stick here has a little thickness. That's the thickness of the sheet of paper. Hey, wait a second. Circumference is 2 pi r. What's the radius of that circle? That's the x value we picked to draw the stick, isn't it? So our circumference is really 2 pi x. And then our height is our y value. And the thickness of that slice gives me an integral. Now, here's the absolute best part about this integral. This integral is in terms of x, which means it starts and ends where our curve started and ended. Holy crap, this works! Instead of slicing horizontally or vertically, I slice in a bunch of concentric circles. And I build up this shape by building one layered circle inside another. More circles, more approximation gets better and better. Let the limit of the number of slices go to infinity. I have an integral instead. And then my cake is made up of slices just like this. That's the one I drew in red in our example picture. But I know how to do this integral. This integral is actually relatively straightforward. 2 and pi are constants. Pull them out front. Take that extra x, multiply it in. And the resulting integral is all power rule. And power rule integrals are fairly straightforward. The antiderivative of 2x cubed. Aha. It would be 2x to the fourth over 4. Simplify the fraction, I get x to the fourth over 2. What about this? The antiderivative of x to the fourth. Plug in 2, plug in 0, subtract. 2 to the 4th is 16. 16 over 2 is 8. 2 to the 5th is 32. I'm dividing by 5. Put in 0. 0 to the 4th is 0. 0 to the 5th is 0. So I end up subtracting 0. I need a common denominator. 8 is what over 5? I need a common denominator. So that's 40 over 5 minus 32 over 5. 40 minus 32 is 8. My answer is 16 pi over 5. In general, if I'm making a cylindrical shell around the y-axis, then I'm going to do 2 pi r. The radius is just my x value. F of x is the height. Dx is the thickness. That gives me the volume of my little shell. I literally will draw this thing on the picture to see what my shell looks like. Questions? Here is a similar sort of question. Now, interestingly enough, with this particular setup, I can do this with shells. I can also do this with washers. So you can actually do this problem 2 different ways. First thing I need you to do, every time, is draw me a picture. Even a crappy picture helps, so draw me a picture. What does the region I am looking for look like? Well, that's y equals x. What's the other part? Aha. So I have y equals x and y equals x squared, and they meet at 0 and at 1. Really? Looks like this. Here's my little football shape again. And I'm going to spin this around the y-axis. And that means I'm going to get another piece over here. Like that. I could do this with our cylinders. I could do this with our washers. Because cylinders is a new method, let's try that. The first thing I need to do is draw the stick that I'm going to spin around, right? So I think about a slice, but the slice only goes here. And when I spin it around, it goes like that. It's kind of suspended in midair here. Doesn't reach all the way to the ground. So let's think about how we would integrate this. 2 pi r, that's the circumference of the circle, times the height, dx for the thickness. Two pi, radius, height. What is the radius of our cylinder? It's wherever we drew this mark, right? Well, that's some x between 0 and 1. So my radius is an x. What's the height? Which one's on top? So I take the x value minus the x squared value, like our area between curves, right? I need to know which is on top and which is on bottom. And there's my height. Now, again, I can pull the 2 pi out from, oh, forgot something. Forgot something important. Where does it start? Where does it end? What is the smallest x we can choose and still be in our region? And our biggest x? There we go. But now I know how to integrate this. 2 pi, and from 0 to 1, take the x multiplied in, I get x squared minus x cubed. And now I do the power rule. When I put in 1, I'm going to get 1/3 minus 1/4. When I put in 0, I'm going to get 0. Hey, wait a minute. 1/3 minus 1/4. My common denominator is 12. So I end up with 2 pi times 1/12, which is pi over 6. I don't have to use cylinders to do this problem. I can do this problem in washers if I slice horizontally, because I'm going around the y-axis. Let's draw the picture again. So here's my bad picture. And instead of slicing this way, I'm going to slice this way. So my slice goes across. And I have a circle here, and I have a circle here. And when I pull this out, I get a washer. There's an outside radius and an inside radius. Which curve is the outside radius? X squared. Except the radius itself is measured horizontally, isn't it? So the radius shouldn't be y, the radius should be x. Because from here to here, that's an x value. If I rewrite this equation, what is it x equals? And here, what's my inside radius? Aha. So this integral goes from something to something, and it's pi r out squared minus pi r in squared. And this time it's dy, because my slices go up and down the y-axis. I need one more thing. What is the smallest y value I can use and be inside my region? The biggest one? Uh-huh. There we go. So now I know this integral. Integral from 0 to 1, pi times root y squared minus pi times y squared dy. If when I work this out, I do not get the same answer that I got before, I effed something up bad. So let's see. What happens here when I square the square root? So I have pi times y minus pi times y squared. Pull the pi out. What's my antiderivatives? When I put in 1, I get a half minus a third. When I put in 0, I get 0. 1 half minus 1/3, my common denominator is 6. 3 over 6 minus 2 over 6 is 1 over 6. I got the same answer. I just cut up my shape in 2 different ways. In this version, I sliced it horizontally like I was printing it on a 3D printer, right? This is the way 3D printers print. They print one horizontal layer at a time. In the previous one, I printed it from the middle out in cylindrical rings. There are printers that work that way as well. They actually make a 3D cement printer. It prints using cement and concrete. It prints walls for buildings. The nozzle is 8 inches across. It's an amazing device. Questions? It is possible to do cylinders around the x-axis. It's just really dumb because it's much more complicated than doing washers or discs around the x-axis. So I really only use cylinders when I'm going around a vertical axis. It isn't always the y-axis. And that means there are times when we have to rearrange and figure out what our radius really is. I want to take the region bounded by x minus x squared and 0, rotate it around the line x equals 2. Where do I start? The first thing I should always do, draw a picture. So sketch this graph and draw the line we are rotating around. And then let's draw the rotated piece of the graph. What is the graph y equals 0? Horizontal line. It's not just any horizontal line. It's the x-axis. So I've already drawn that one. What's the graph of y equals x minus x squared? A downward parabola. And that means it goes through the x-axis in two places. Where? Aha. So that's my region. That little bitty bump right there. But I'm rotating it around this line. So when I spin this, it's going to go this way. It's going to move from the left to the right. And that means this piece is going to end up over here somewhere. Like that. What are the two x values where it hits over there? 3 and 4. Because I have to be 1 unit away and I have to be 2 units away. And that means we've gone around the front, around the back, around the front, around the back. Okay, I already ate breakfast, but now I'm hungry. This shape looks like half a bagel, only its flat side is down rather than its flat side is up. Okay. Again, it would be very difficult to slice this horizontally to figure out its area volume. Because then I'd have to solve this for x. No, I don't want to do that. So I'm going to make a cylinder. I take a piece in the original part of the curve that's over here. I take a stick at some x value and I spin it around. And I get my little standing ring. I rotated this around the line x equals 2. And I chose some random x value to make the stick. So I've indicated where I chose it and the axis of rotation. Now, let's think about our integral. The volume integral, 2 pi radius, height, thickness. And literally, I write that formula down first, regardless of what I know r or h or any of those things to be. So let's start here. Now I go back to my sample cylinder, my little cookie cutter over here. And I say, do I know the height? What is the height over here? The height. X is measured this way. Ah, the height's going to be a y value. The y value is right here. Radius. Now here's where I think this drawing on the right makes it a little easier. The radius goes this way, not this way. There's my radius. All right, if I just said x, I would think about measuring from x back to 0. But I'm not rotating around 0, I'm rotating around 2. So how do I figure out how far this distance is? Aha! The right number minus the left number. There's only 2 more things I need. What is the smallest x value that I can use and still be in this piece of the graph? And the biggest, and still be in this piece of the graph. See, I know this goes all the way to 4, but the original piece of the picture only goes from 0 to 1. And that's where I'm going to choose my x. But now I know how to integrate this. I just have to multiply it out. So the fact that I wasn't going around the y-axis meant that my radius changed. And that is important because it is the idea that allows me to say, I don't care where I'm rotating around, as long as I have a line that I can rotate around, I can figure out what the right radius is. Multiply this out. I get 2x minus x squared minus 2 more x squared plus x cubed dx. And I'm back to power rule again. Thank you very much. Antiderivative of 2x. Antiderivative of 3x squared. That's what I've got here, right? Antiderivative of x cubed. When I put in 1, I get 1 squared minus 1 cubed plus 1/4. When I put in 0, I get 0. These ones cancel, so I get 2 pi over 4, or just pi over 2. Questions? Yes.
Can you probably distribute it to minus x and
Sure.
I don't actually.
It's 2x minus x squared minus 2 more x squared plus x cubed. So I just combined those to give me this. You put that off in parentheses, so it doesn't look like I'm setting that to be part of the equal signs. This idea can be used on any object that is rotated around any line, as long as the object is entirely on one side of the line. If I'm trying to rotate something about a line that cuts through it, then part of it will be on one side, part of it will be on the other, and I won't be able to figure out the shells will be on 2 different sides at the same time. That's bad. So as long as my shape is completely on one side of my line, I can use this idea. As a matter of fact, there's a really nice result attributed to a mathematician by the name of Pappus. The volume generated by rotating an area around a line, where the area is all on one side of the line to begin with, is the product of the area of the shape times the distance traveled by the shape's center of mass, also known as the centroid. And that centroid will travel in a circle, so I'll get 2 pi r times the area of the shape. This, by the way, comes from slicing up our area in an even different fashion. We sliced it into circles, right? What if I actually sliced it into slices of cake? Little slices that went around. Then I'd add all those slices around, and that would give me the circumference of a circle. We will actually show how to do this when we show how to find a centroid, but to find a centroid is going to have to wait for another day, because I just ran into it. Monday is question and answer day. Please come with questions. If you wait until Monday to start this assignment, it will be exponentially harder than if you start it over the weekend. Have a good one.